Welcome to The Explainer, where we break down big ideas. Today, we're digging into a data structure that honestly powers a huge chunk of the modern internet. And it all comes from a super clever paper from way back in 1995. Really, it's a story about a very efficient librarian and an absolute mountain of data. Okay, to really get this, let's picture something. Imagine a bank, and it's processing 1,000 transactions. Not an hour, not a minute, but every single second. And this isn't just about storing the data. No, each of those transactions has to be indexed immediately in some massive, ever-growing history table, so you can actually look up your account activity later. It's a relentless flood of information. So, here's the big question. How do you possibly keep up with that tsunami of data? Answering this is absolutely crucial because, as the original paper pointed out, getting it wrong is incredibly expensive. We're talking about potentially doubling the cost of your entire disk system. For a long time, the standard go-to solution was a super reliable data structure called a B-tree. A good way to think about it is like a very meticulous librarian who follows a file-as-you-go system. Very organized, but also very, very busy. So whenever a new transaction comes in, our B-tree librarian immediately stops what they're doing, walks all the way to the exact right spot on the disk shelves, finds the correct page, updates it with the new info, and then writes that page back. It's super precise, sure, but for every single new entry, that's a whole separate round trip. And with 1,000 of these random inserts happening every second, you can see the problem, right? Our poor librarian is doing 2,000 separate disk operations, a read and then a write for each one. They're just constantly sprinting back and forth across the entire library. This random access becomes a massive, massive bottleneck. And don't just take my word for it. The original paper put it pretty bluntly. Just to keep this index up to date, you might have to buy as many disk drives as you needed for all of your actual data in the first place. I mean, that's crazy. It was obvious there had to be a smarter way to do this. And this brings us to the hero of our story, a new, much more efficient librarian with a totally different system. This is the log-structured merge tree, or LSM-Tree for short. And this librarian, they do not run to the shelves for every single new book. The big idea behind the LSM-Tree starts with something simple, an inbox right there on the front desk. Now, the technical term for this is a memory resident component called the C0 tree. All the new data just gets dropped right there first, where, access is basically instantaneous. And the implication here is profound. I mean, this is huge. Placing new entries into this inbox costs almost nothing in terms of I/O. It is unbelievably fast, precisely because our librarian doesn't have to make that long, costly trip to the shelves every single time. Okay, but you're probably wondering, what happens when that inbox gets full? And that is where the real magic of the LSM-Tree happens. This next part is the core of its incredible efficiency. So, instead of filing things one by one, our efficient librarian waits. They wait for the inbox to fill up. Then they take that whole sorted batch of new information and merge it with the main collection on the disk shelves in one single super efficient trip. This whole process is called the rolling merge. And this chart really shows the first big reason why this is so much better. A random disk access, that's like making a separate trip for one book. A sequential multi-page access is like grabbing a whole cart of books, walking down a single aisle, and shelving all of them at once. The paper estimates this simple change makes the I/O about 10 times cheaper per page. So, just to be super clear, there are two separate wins happening here. First, we change how we access the disk. We do it sequentially, which is way more efficient. And second, we batch all the work together, so we do that efficient access way less often. It's a 1-2 punch of efficiency. The paper even gives this a name. Basically, the idea is the bigger the batch of new entries you can merge for each disk page you touch, the cheaper each individual insert becomes on average. You're spreading the cost of that one trip over many, many items. But, in the world of engineering, there is no such thing as a free lunch. This incredible write efficiency has to come with a trade-off. It has a price. So let's go back to our librarian. If you walk up and ask for one specific book, where do they look? Well, they can't just go to the main shelves anymore because it might not be there yet. It could still be sitting in that inbox on the front desk. And that is the trade-off right there. To find any piece of data, the LSM-Tree has to check the in-memory inbox, the C0 tree, and then it has to check the on-disk shelves, the C1 tree. This makes finding data, what we call reads, a bit slower than in a B tree, which is optimized to have one and only one clear path to everything. So, why on earth would you accept slower reads? Well, it turns out this is a fantastic deal for applications that write new data way more often than they read old data. Think about things like system logs, performance metrics, or those giant history tables we started with. And that brilliant trade-off, that very specific choice to prioritize writes over reads, is precisely why this idea, born in the mid-90s, became so unbelievably important decades later. You see, this core principle of deferring and batching work was perfectly suited for the data explosion of the internet age. It became the absolute cornerstone for so many modern databases that power the biggest applications we use every day. All right, let's sum it all up. The LSM-Tree sees the problem of expensive writes and solves it by cleverly deferring work into an in-memory inbox. Then it uses a rolling merge to batch those updates efficiently, all while accepting the trade-off of slightly slower reads. Ultimately, the log-structured merge tree is such a powerful reminder of a timeless principle in computer science, and honestly in life. Sometimes the smartest thing you can do is just wait and do the work later, but do it all at once. It really makes you wonder, doesn't it? What other complex problems could be solved not with a more complicated machine, but just with a more patient and a more efficient librarian?